Today we are working on 10.1, which is exploring quadratic graphs. After today's lesson, you will be able to graph quadratic functions of the form y equals ax squared and graph quadratic functions of the form y equals ax squared plus c. A couple things first before we get started with some examples. Quadratic function is a function that can be written in the form ax squared plus bx plus c. This form is called the standard form of a quadratic function. Notice very similar to what with the last chapter we worked on. The exponents go from 2, 1 to 0. And that is in that standard form piece. But with a quadratic function, you're just going to keep it as an x squared, an x, and then your constant. Now, we're going to talk about a parent function. So this first piece here is talking about a parent function. And what that means is everything's going to kind of relate off of this x squared piece. A graph, an x squared, whenever you see something squared, what's going to start to register is that is going to create a parabola, which is what, if you just ask, describe this graph here off to the right, you would say, looks like a U, where maybe when we did our absolute value, we know the absolute value of x is going to create a V shape, where this is similar to a V, but it's more of a U shape. It doesn't come to that exact point. So, just so you have the right vocabulary and that you're kind of on the same page here, this U shape is what we call a parabola. And having it just x squared by itself, so just your a would equal 1 here. And if we're looking at this form, y equals 1 x squared. This x squared is what we call our parent function. That is as basic as it gets. We're going to get a little more complex towards the end of this lesson. So some FYIs for you. You can fold a parabola so that the two sides match exactly. And this will be important when we come to graphing it. This property is called symmetry. So you can fold a line on the axis of symmetry, and these are going to match up. So on here, our axis of symmetry, my straight line there, is going to be right here on our y-axis. But notice whether I go one spot over and one spot over, about 1.5, 1.5, almost 2, almost 2. So this axis of symmetry, understanding symmetry, symmetrical, that it's the same when you fold it. Also, some other basic information that we will talk about is our vertex. So in our vertex is where the parabola meets. It's going to be that point, that center. And we're going to have, we need to be able to identify minimum, maximum, and we're going to do an example of each here in a second. But understanding when your a value, and I probably should start over here, your a value is bigger than 0, this vertex is going to be a minimum, and this is what it's going to look like. So that a value is bigger than 0. So 1, 2, 3, 4, continued. Whenever it is big, a positive, I guess is what I should say, then we are going to have a graph that opens up like this. Now, this vertex right here, it's at that point where it comes to, and it's on the axis of symmetry, which is another important piece, the axis of symmetry, that this is the lowest point. So because this is the lowest point, it's your minimum, so it's your minimum point. Where here, my a is less than 0. So if my a is less than 0, it's like a negative, -1, -2, -3, continued on. So if a is less than 0, notice here, and kind of ignore how I just flipped this graph, but this is the shape we're going to get. It's going to be a down. The U is going to be flipped downwards. Or my parabola is going to be flipped downwards. So here, this is my highest point right here at my vertex. So since that is my highest point, that is my maximum point. And we'll get into this, identify the vertex of each graph, tell whether it is a minimum or a maximum. Alright, vertex. Now, at this, when I'm looking at this one, my vertex is going to be at that point right here. And notice my axis of symmetry, line I just drew. I could fold this parabola on this line of axis symmetry and it would line up. So here's my vertex. What is this order pair right here? Well, it is at 1, 2. So my vertex is at 2. This is my highest point, so this would be my maximum. So vertex 1, 2, and it is a maximum. Now, looking at example B here, find my axis of symmetry. Where is it meeting to? Right here. What point is that? 2, -4. And it is my lowest point, so it must be my minimum, which it is. This next example is asking you to graph this. So they're going to give you this and say graph it. So what we do is we create a table. And we have our x's, and most of us will just create just an x and a y table. Plug in my value for x, and what do we get for y? Well, 1/3 times 0 squared. Well, 0 squared is 0. 1/3 times 0 is 0. So this is kind of showing you the work, the math part. And then here's what we're looking for. We get 0, 0. Plug in 2. 2 squared is 4. 1/3 times 4 gives me 4/3. And 3 squared is 9. 9 times 1/3 is 9/3. 9 divided by 3 is 3. So here's my order pairs, which they have done nicely as well in this column. What we're going to do is we're just going to graph those order pairs. So they've already done this for me. So here we have 0, 0, and 2, 1/3 is right here in red, and 3, 3, 3, 3. Now, what is beautiful about this, about a parabola, is that axis of symmetry, because we can fold this here in half along my vertex, that straight line there, we will get on the other side the same points. So what we do is this is 1, 2 spots over, so go 2 spots over, and it's straight across. Here 3, 3, so we're 3 spots over, 1, 2, 3, and I have my new point. Then once you will only have these 5 points, you can connect them and make sure that we don't come to a point here. Alright, it's that would be considered a absolute value graph of V-shaped, and we want a U-shaped through here. This next one says order these graphs from the narrowest to, or the widest to the narrowest. So, knowing what we know, this one looks pretty wide, I would say, and then it's kind of getting a little more narrow, and then probably in between. So I'm going to roll through what they have here. It says one of the 3 graphs, y 1/2 x squared is the widest, and -3 is the narrowest. So in order, you would put them in this order. Now, what I want to emphasize here, and what I want to make sure that you see, is when your A value, A value, we talked about being positive, it's going to open up. If it's negative, it's going to open down. But now the width is what we're looking at. When you have a fraction, it is going to be wider. It's going to continuously get wider and wider as your fractions. Now, when you have here a 1 and a 3, 3 is bigger. We're looking at that, so it's actually getting narrow, narrow, narrow the bigger it gets. And then your -1 is like your standard 1. So that's just some good info, being able to identify graphs and types of graphs and kind of what the different shapes are going to be looking like. In example 4 here, it says compare these 2 graphs. So what we would do is we create a table for my values. So plug in 2 into my first. So just notice I pulled this one here. This equation gets pulled here. My first value is 2 for my x, so plug it in. 2 squared is 4. 3 times 4 is 12. Now, 2 squared is 4. 3 times 4, 12. Now we have to subtract 2. Minus 2, we get 10. Plug in 1, you get a 3 and a 1. 0, a 0, and a -2. On your way down. Now, they have graphed these for me already. So you can see here, this red one, 12, 10. We are, let me rephrase that, it should be 2 to 12, so over 2 up 12, which is way up here, and then 2, 10, which we can't even see on this graph. So we're going to skip it and go on to 1. 1, 3 is my first order pair. So 1, 3, I can see here. And 1, 1 is going to be the one in blue. So 1, 1. So I can just rewrite these if this helps you to see. You have 2 sets of order pairs. Alright, so there is my 2 sets. We have these sets here, and then the other set. You're using the same x's, just getting different y's. What do we notice here? This is really, really neat, that these 2 graphs are going to be the same, except everything is shifted. My vertex, instead of being at 0, 0, is at -2, but otherwise they're identical. So, because this is telling you it's shifted down 2, it's from that -2 piece. So it's really just shifted down 2, and we can see that in our graph. Now, if this was a +3 at the end, let's say it said 3x squared plus 3, I would take my red as my parent function, that original that we talked about at the beginning, and then this would be the one I'd have to graph in blue. If it was +3, what would happen is we'd move it up 3. 1, 2, 3. Start my point here. The blue vertex would be here, and then we'd create that same, which just doesn't look quite, but it would be the same shape as the blue one, but just shifted up 3. It's kind of understanding and exploring this the quadratic graphs, and that piece is important.